And that's it. We're live. So, hello. Welcome everybody to this webinar from SCIA Engineer. I'm happy to see that you joined us and decided that this topic can be interesting for you. So as every SCIA Engineer webinar, it's given on the GoToWebinar platform. You guys are muted because these sessions are recorded and they always come available for free for anybody to rewatch at any time on our YouTube channel and also on our website. But if you do have questions about what I'm telling you, don't hesitate and put it in the questions box. It has a little question mark, I think, on the top right of your screen. So you can click it and type any questions you may have. I will try to reply to them at the end of my session. I'm alone today, so nobody can answer while I'm talking, unfortunately. But I will try to answer it at the end. And if not, if the time for our webinar is up, then I will reply to them via email a few days after this webinar. Yeah. So the topic for today is steel design according to American design rules. I will give a little bit of a general overview of what's available in SCIA Engineer for steel design according to American rules, or for European people needing to use American design rules, maybe what to look out for and which options to choose also. And then I will try also to focus on the recent improvements on version 25, what has been changed and added there, and put some more attention on those topics. I apologize, I'm actually quite ill, but I think it seems to be going. I didn't want to cancel the session last minute. I hope my voice will keep the whole session alive. And yeah, I might be maybe less bubbly or less quick in finding the English words than usual, but I'll do my best. So me, I'm Jael Verkammer. I work at SCIA now for already 7 or 8 years. I started first at the support of SCIA Engineer in Belgium, where I replied and gave trainings to all of our customers. And now I am in the product management team, where I'm responsible for the developments according to material design. So the steel design, aluminum design, everything in both American design codes or Euro codes. So that's what I busy myself with. And with that, I will go on to share my screen. Hopefully the correct one. Share screen. This one. Share. Okay. That seems to be working. Good. Then let's talk about steel design and American design codes in SCIA Engineer. Yeah, so I made a tiny pre-example because, modeling something in SCIA Engineer, while it can go quite fast, it would still take up a big portion of time in the webinar, and there are plenty of videos that will explain to you how to model stuff, or maybe most of you also already know how to model in SCIA Engineer, and it's not really dependent on whether you're modeling for American codes or Euro codes, except maybe the unit system. So we can maybe look a little bit into that part. First, I think for the unit system, if you want to work with the feet and inches system, I think the easiest is when you are starting a new project, in the project data on your unit set, to choose the imperial format. then all of the standard American imperial system units will be set as default when you open the project. Of course, you can still go into the unit dialog either straight here from this menu or from up here, manage units, and for everything change the unit that's being used. So if you want to use feet here or yards, whichever to your liking, you can change these, and you can also save these as your user default settings or some sort of settings file. If you have different kind of settings you like to use for different purposes, you can save these in a file and then load them later some other time when you want to use these units for a specific project. Then another part for the project settings, of course, that's important, is to choose your national code correctly. So if you want to design according to American design rules, we will have to select the IBC here. If it's not IBC, but for example, Eurocodes or the Brazilian codes, you click the three dots, you click add, and then you can add the code that you would like into the project and then change it. But for now, for me, it's already set to IBC, so I will keep it that way. And then once you have the IBC set here, also for the materials that you select, the American steel grades will be available instead of whatever other steel grades from the code you had selected before are there. Same for concrete, etc. But I will not be talking about concrete today in particular. Okay. So yeah, that's basically for the start of your project, the important part. To set correctly, and then you can just go ahead and model your project. That's completely unrelated to what design code you're using. The first difference comes then with the defining of the loads. Do I have some? I'm trying to add a surface load on 2D, but only getting the free surface load. I think I'm putting the wrong words. Anyway, if I'm not finding it here, you can also use the input panel maybe for looking at the loads, point loads, surface loads. That's the one I'm looking for. Yeah, surface load on 2D. Okay. Don't know why it wasn't appearing there. But yeah. So loading also, it works perfectly the same way. Only the value is, of course, in the unit that you have chosen. And by default here, this is the unit chosen by SCIA Engineer. Of course, you can change it. I have defined some loads already in this project. We have some very basic loads, really. A wind load, a roof live load, just a live load. This one is empty. And this one is the self-weight. As you can see, I will add here self-weight. This is empty anyway. Okay. So far, we just add load cases. You can add the loads in there. So depending here which load case you are, this is the load case I will add things into. Yeah, so if I want to add the loads to my wind load, I will just put maybe now he wants to do, yeah, now he wants to do the surface load on 2D. For example, I could add it in here on my load panel, and it will be in load case 5 only. But yeah, let's remove it. Maybe we don't really need it. My surface load. Okay. Load cases. So once we've defined our load cases and the load in it, important thing to look at is the action type. So if I made a load case of an action time permanent, it will get put into a permanent type of load group. The load groups are what affects as what type of load it is considered for combinations, and this affects the coefficients given to it. So if your load group is in a load case is in a permanent load group, it will get the coefficients for permanent load cases in the combinations. And yeah, if you want to put it in a variable load group, you need to put this load case as an action type variable. And then you'll be able to put it in load cases which are of the variable type. And there I can choose then which type of load I'm working with. So I had the live load, I have the roof live load, and this is one of the novelties also that's been added in the new version, is that we've updated actually the rules for combinations, and I believe some types have been added, some categories have been added, or some coefficients have been changed. So this is new in version 25 of SCIA Engineer. But yeah, for you, you just select the proper type, and then the proper rules for combination for coefficients according to ASCE 722 will be applied in the combination afterwards. Yeah, for live loads also, you can choose to apply yes or no live load reduction in your combinations if you want to. Okay. So we define load cases in which we put the loads, and then we define load groups for defining how which coefficients are applied to these loads in the combinations. A second thing why we define load groups is, for example, I can have several loads in the same load group. For example, I can have wind from multiple directions in the same load group, and then I can define some kind of relationship. Because the wind, it will always blow just from one direction. So in every single combination, I only want to consider one wind load direction. In this case, I will put them all in the same load group and set their relation as exclusive. Exclusive means that in every combination, only one of the load cases in this load group will be considered at once. If you put them together, then all of the load cases of this load group will always be applied at the same time. So we'll never find one without the other in the group. And then finally, standard, we will just consider all possible cases. One is there, the two are there, the other one is not there. Everything gets combined in any possible manner. So that's what load groups are for, defining the relationship between the load cases that are in the same load group and defining the load type and the coefficients to be applied for combinations. And then the next logical following are the combinations. And you will see, well, I didn't start it from scratch with you guys, but I didn't actually create these load cases, and it tells you so in the name. They are automatic. So these load combinations are automatically generated, and this is something that you can choose also in the project settings, whether you want or not to have automatic load combinations, but also which type of load combinations. So for American steel design, we have two possible methods of doing our design and verification of the structure. One is according to the ASD method, the allowable stress design, and the other one is according to LRFD, so load and resistance factor design. The LRFD, load and resistance factor design, is one that's most closely related to what's done also in the Eurocode, where we will apply safety factors both on the loading side of things and the design side of things. So we will take into account uncertainties at every level of the design where they can arise. And on the other side, in the AISD, allowable stress design method, we will just consider the loads as is, no safety factor applied on top of them, but we will greatly limit the stress allowed in the structure. So there will be just a big coefficient at the end on the stress in the structure. So we will be much lower than what we allow in LRFD. I think today LRFD is also for America the most applied method for steel design, and this is why it is the default choice. But it still happens that AISD method wants to be, you want to use it, and in this case it's still supported. In that case, if you want the automatic combinations, you go in the project data. You don't see me type anything. I have some shortcut set for it. I can also look for it here. And as you can see, I have here the letter P set as a shortcut to open it quickly. Then you go to the load. And here I can choose to have the AISD combinations. In this case, if I open the combinations menu, you will see that now my automatic combinations are according to ASD. Sorry, all these shortcuts of words are confusing. Now, if you see that actually nothing has changed here, right? Earlier I had the LRFD and they also all had the coefficient 1. Now I have ASD, they also all have coefficient 1. What you see here is just the automatic code combination setup. And it will automatically in the background apply factors on it and combine the load cases I have put in here. If I want to see what actually happens in the background, I can explode to linear. This will create linear combinations, as we call them, of all of the subcombinations that are in this automatic combinations. So actually all of these individual combinations are considered inside this one. So if you explode them to linear, you can see them, but there's absolutely no need to do so, right? I will also delete them after. It's just so we can see what's in there. And yeah, here this is for ASD, so we see that everything is applied with coefficient 1 or even with a reduction for the live loads that are added and for combination of live loads, which are less likely to happen at their full combined forces. And if we compare it to the LRFD, maybe. Yeah. So if you don't want these automatic combinations, you can also tick off this little box and they will no longer be automatically generated. So if this annoys you, you want to do them yourself, also possible. And if I explode these to linear, we see that these have actual safety factors applied to them. So you can see the difference in design approaches of the two methods. Okay, so here we are for combinations. And so you see these are set at 1, but the automatic coefficients get added in the background. If I were to change these, I think I can if I put on the active coefficients. And I change this to 2, I would just be considering twice the live load in my combinations, again with the other coefficients added on top of it after. So don't start and input your own 1.5 or permanent loads or whatever, because else you will get another 1.5 added on top of it in the background, which is not what we want. If you want to do that, just don't use any code combinations and create your own combinations, I would say. And then I saw on my paper, because I was going without my paper earlier, that I did put some little info on the modeling side, which is about cross sections. Because generally between America and European design, we use different ranges of cross sections. Both of these are available in SCIA Engineer. And also in version 25, we have updated our profile library for the American, the American catalog of profiles. So if you are doing steel design, it's very much recommended, and especially if you're doing it for American codes, to use the thin walled geometric type if you are entering your own parametric kind of section. So these ones allow you to yourself add some sizes in inches and create your own profile if you want to use something not from the profile library, or use the pairs if you have a paired section, or a sheet welded if you have welded sections. Any of those are fine, just not the geometric shapes, and also not the general shapes unless it's an actual general cross section. So that's possible. But if you want to enter your own kind of values that are not from the standard library, use the thin wall geometric if we have the shape, because for the American design, actually the shape matters into which and how the checks are executed. And therefore it's important for SCIA to know which shape type it is. If you enter a general profile, then it will go to the general case of the AISC design, which is also absolutely what you want, but don't use the general cross-section input for making an eye section, and just use the thin wall geometric so that SCIA is aware it's an eye section. Yeah, and then I've used here also, if you want to filter out from the giant list of options of cross sections, the ones you are actually looking for, in this case specifically American profile libraries, you can set the profile filter to America. And here you can also see that we have updated our shapes database to the 2023 most recent version that was available. So that's, yeah, well, not everything I wanted to say about cross sections, but a big part. My final part goes about the classification of the cross sections. So you can find in your cross section some information here about the initial shape. This is a definition of which one are internal parts of the profile, which are fixed parts, which are external parts, are they symmetrical, and these are used for the automatical classification done in SCIA Engineer. Of course, if I select the American, the IBC code at the start of my project, then this classification is done according to AISC 36022. So 22, that's new from version 25. We have updated to the latest design rules here. And you can find a full output of this classification, even with the formulas, and for each part some definition and the outcome of the checks. Yeah, okay. I think that's the most important part we had on the input loads combinations. So then the next logical step in our journey here is to calculate the project. This is also completely similar to anything else you would do for any other available design codes in SCIA Engineer. But yeah, I like to focus still on it. I think most importantly, when you first have modeled a project, is to go look at the result and look at the 3D formations, because for me, this is kind of the best check for did I make any modeling errors? So if the 3D deformations look logical and no bars are deforming differently, or you will quickly see if something is not properly attached or anything else. So yeah, that's some important kind of thing to check always. Aside from this, of course, these are just the results from a finite element analysis. They are the same whichever code you would apply. That means also that for American steel design, all of our other functionalities are available. So you can do a nonlinear calculation. For example, I have some bracings here. If I want to consider that these will not take up any compression forces in the analysis, I can run a nonlinear analysis. Or I can run a stability analysis to check the stability of my structure, check the critical load factor at which my structure will buckle, and use these to determine some buckling factors for specific columns. I can do also a seismic analysis, so calculation of seismicity loads, seismical spectra. And all of these actually work the same for all design codes. They will do a finite element analysis and give us the same kind of results in this menu. And these results we can then use to go into more American specific results, which we will find in our steel design. But before we go into steel design, it's really, really important that we think about buckling and buckling settings. For getting any correct results from your steel design, it's really important that we put the correct input in there and define the buckling systems correctly. Generally, SCIA will automatically identify which are the supporting nodes for buckling and therefore which are the spans in which buckling can occur and their sizes, and it will even calculate a buckling factor for you. But for some of these, it will not go so nicely automatically, so it's important to check. If I look at this column in particular, we will see that, let me zoom out a little bit so we can see where we are in the structure. I have a part of the structure hidden. I will show it to you later, but we are here at the corner column. And so I have some nodes up here that are not connected to anything. So you see that he automatically notices there is no support here, and these are not considered as supports for design. And then on this level and this level, we have a beam arriving, restraining it. So our buckling span will be in between those two, and then above it. And then also here to the bottom, there again is one extra node, but nothing arrives there to stabilize it, so it isn't considered. Then in the other direction, we have the same at the top. These two are not considered. This one is, because there is a beam. The other one is also, and here at the bottom, yeah, we see that the bracing actually doesn't arrive fully in the bottom node, and he thinks that this node is actually stabilized. Now, the distance is not very big, so it probably will not change much about the structure, but in any case, this bracing doesn't have enough stiffness to hold it back, so we could consider that this buckling, this node is not restrained for buckling, so I would probably adapt this. So this is buckling in the principal axis, and this is a in the principal axis with the highest stiffness, and this is along the weak axis. And then we have torsion stiffness. I would say these are also correct, and these are the support points for lateral torsional buckling, which also seem correct to me. And then finally, you have also the ones for deflection in both directions of the beam that you can change. Okay. If you have like a lot of similar columns, you can actually share these settings with the other columns. Maybe I can close these results. So did I save it? I didn't save my changes. That's not very smart. Be save. So I could call this one column. Okay. And then if, for example, this other column had the exact same situation, which now it doesn't, I could go into this column and also assign it the system and buckling settings column. Now, in this case, it doesn't, because it doesn't have the bracing arriving, creating an extra node. So they cannot share buckling settings because they don't have the same amount of points arriving on them. If you want to quickly select all the ones which could share a buckling system, there is this option here, steel, and you can see it's divided in 3 regions. If I click expand selection, based on that, I can select all the elements which could share a buckling system. Yeah, this project doesn't really have a standard column in it. It's quite variable, so I would basically have to look at about every single one of them in particular to define their systems. But it's really important because, for example, here for this one, this bracing will be seen as a support for buckling, whereas the bracing doesn't take any compression, maybe. And then, yeah, this LTV length also will be divided. Everything will be divided by this node, and therefore my results will be optimistic when they should be. So it could be dangerous to have wrong results. So very important to look into the settings of your buckling before going into design. Other settings that we have are the IBC steel setup, which is the setup for both the buckling and the design of our steel. Most of these settings are buckling default settings. So actually we can change all the default values from the buckling settings of every individual beam. So here all the beams that are left on a default setting, if I change the settings here, it will change also the settings for the beams that have a default setting. Yeah. And then there are some different settings for the calculation of buckling factors. So as I told you, SCIA will calculate for you buckling factors if you so desire. These are the formulas that he uses for it, depending on whether you've defined your structure to be sway or non-sway. In each direction, it will use a different formula and come up with a buckling factor for you. If you don't want it, you, for example, want to consider a factor of yourself, you will have to put it on factor and in your beams themselves. So I will go here to the default one. Yeah, so if I change this one to factor, the default will be 1 everywhere, and you can actually change and consider your own factors if you're not happy with the buckling factors that have been calculated by SCIA Engineer. So theoretically, if I want to consider a factor 1 everywhere, I could leave everything on default and then set these to factor everywhere, and it will automatically choose the 1 factor everywhere. But okay, these are just the buckling settings and the setting for calculating buckling factors or not. The most important setting of all is the method to choose for the steel design. And this one should just match the one that you've chosen for your combination. If you're doing allowable stress design with the combinations for LRFD, then you will greatly over dimension your structure because you will not allow for much stress, and you will put high safety factors on your loads. So yeah, well, this would be the better way to do the error because the building won't collapse, but still it will be a high cost for no reason. And other way around, if you put the LRFD design methods, then you use the ASD combinations, you will not have any safety factors on your loads, and therefore, you will um, overestimate your structure, which is of course more dangerous. So be careful to consider the proper methods for the design in the setup. And by default, this is LRFD. And I need to warn you that changing the combinations, the automatic combinations, will not change the default in the steel setup. So if in the project settings you have chosen here to have the ASD combinations, when you go to execute the steel chuck without looking at the steel settings, you will run it for LRFD design even if you chose a ASD type combination. So yeah, that's really, really important for you to be attentive to. Let me select a member for running the check. Of course, you can see it. Oh no, this is the combination I choose, so you don't see it here. But in the output, we should, yeah, you can see that we are executing the LRFD check or the ASD check. So this hopefully should alert you as well if anything is going wrong. Yeah, so really, really important. And another thing we can change is to overrule which chapter is being used for the combined check. So whether you want to use section H2 or section H1 for the combined check. If you change it here, it will be changed for all the members except the ones with specific member data. If you want to change this for one member in particular, I already spoiled myself, but you can use member data, where you can change this setting and choose one specific member. Or I already had one selected, so this member will now follow what I've defined in this data. So here I said not to apply H2. If now in the steel setup I say to apply H2, it will do it for all of the beams except this one in particular where I said not to do it. Or the other way around, of course, whichever way you want to work. Okay. So I already showed it briefly, but to execute the check, we go here to steel strength check. Again, I will reiterate, make sure to have the combination that matches the method of the design you've chosen. And then we can run the check for one member in particular and look for detailed outputs and with tables and formulas. That's the most extensive output that we can ask for in SCIA Engineer. And you will see that there is not really a chance you would ever wish for a more detailed output than this one. Yeah, so we are doing the LRFD check. We can see which member, the length of the member, the material, and the overall check. We can see which load combination is causing this critical check. We have the safety factors that have been used, the material information. Sorry, I skipped a bit too quickly. Yeah, the information about the material. And then there is this little weird telling. So yeah, you all know that SCIA is initially a European software, and yeah, we have the. I'm not finding my words. I warned you up front that I would have some difficulties. Let me have a drink and maybe it will come to me. No, I just forgot what I was talking about altogether. So usually In Europe, we will have the x-axis as the axis of the beam itself, and therefore the perpendicular axis to it are called y and z inside SCIA Engineer. And as the input is common for both for all design codes in SCIA, yeah, we cannot really change the names of the axis references inside of SCIA Engineer, the modeling itself. But for the check, we choose to follow the definition from the design code so that it's easier for you to to compare the results from SCIA Engineer design to the codes themselves or some other design if you wanted to, and to be able to follow the code and follow what's happening into SCIA Engineer more easily. But therefore, it's important to know that whatever in the check is called x-axis. In the actual SCIA Engineer window, it's called the y-axis, and also for the buckling. And whatever is called Y is called Z in SCIA Engineer. So earlier, when I showed you the buckling settings and directions, you saw that they had a Y and Z direction. And in these checks, these will therefore be X and Y. I hope that's a bit clear for you. And then these are the internal forces for the combinations that led to our critical check. And then finally, we see something we already saw before. This is the classification of our cross-section according to AISC 36022. This part is exactly the same as what I showed you earlier in the cross-sections menu. Except here it's done for the load combinations that are present here. You will find the same detail level as you have seen before in the cross-sections menu. And then we go on to follow the AISC check. We can see which article it's following and therefore which formulas are being used for the check. This depends on which type of cross-section you have. So again, that's why it's important to use the thin-walled cross-sections for your design so that the proper articles and checks are executed later in the design check. I don't think I need to go into detail. Everything is explained quite clearly. You have the names of every check, you have the formulas, you have the article from which they are coming, the states. You can find absolutely every single detail and know how every single value is obtained here. So I hope that this is clear to you. Where everything is coming from. And of course, this level of detail is a bit too much if I want to put in some summary for every element stating that they are passing or not. Let me say for all here, I don't want all of these details. So in that case, I can change the output level to brief. In the brief output level, let's do an extreme per cross-section. Let me do a report preview. Yeah, so here you will see actually per cross-section type, you will find all the cases that generated one of the checks to be maximized. So it's still quite a lot of information. So for every single cross-section, you will see actually 1, 2, 3, 4, 5, 6, 7, up to 8 different results leading each to a highest unity check, and my table is still quite long in this case. If rather we want to just see an overview table that shows just the overall highest unity check per cross-section or per member, we can go here into components. And there you can choose which components you want to yes or no add. So I could have 2 of them if I wanted to, or if I, like in my case now, I would just want the overall highest unity check, I will just activate this one. Let's do per cross-section first. And open the preview. Yeah, so now each cross-section here is different per cross-section, we will see the highest unity check that has been found in the model. As you can see, some of these are not quite optimized. So here the 615 barely has any load. This is mainly because I just whipped some project together with random loads and didn't really look at it. But if we wanted to optimize this structure, a very easy way to go for it is to use the Autodesign function. To use the Autodesign function, we need to be looking at the results for one specific cross-section. So that's why he says that the filter will be switched to cross-section. He's talking about this filter here. Here I can choose a cross-section. I don't remember which one it was. It was W6 something, but I'm not, oh, 615, this one, for example. Okay, let's look. Oh yeah, oh, it's one of those choice ones. Okay, yeah, they're barely used. But if I wanted to optimize this, maybe it's already quite small and I just didn't apply load on there. But let's do it anyway because the function is the same. I can go here into Autodesign now, as I tried earlier, and I can search for the optimal section in my library for getting a check as close as possible to 1. In this case, it's just taken the smallest possible section in the library because there is just no loads on this beam. So yeah, unfortunately, it's only getting us to 0.5. Maybe I can use some other shape to get a better outcome. Are you more? It's 1.02, so it's already almost there. Probably the Autodesign will just give us the one size up. Yeah, there we go. We just got the one side up out of the list. This is sorted by height, so maybe I can, I don't really care about how high my profiles are. I more care about the total weight of my structure. So then I will sort the list more by the area of the sections, and then he finds the first, the lowest area section that will satisfy the check. Okay, and it will directly be applied in my model. So that's the Autodesign. Wow, time really flies. I thought this would take me half an hour or something, and here we are 48 minutes later. Final thing to look at is probably the serviceability check. Nothing really particular there. You can, of course, choose the serviceability type combinations. If there's no combinations here to select, it's because you haven't defined one. So there's a smart filter here that you cannot choose an ultimate type combination for executing a serviceability limit check. Yeah, let's select the beam. And this one will check the deflections both in Y and X directions. Here they are really good. Maybe let's take a bigger one with a larger span. It might not even. Maybe you look tiny with a lot of load. No, also really fine. So in this case, my project doesn't seem to have much issues with deflections. The same, you can find an output here where it will show you the deflections in both directions. Again, the X and the Y convention is used for the deflections, or so X being Z and Y, X being Y and Y being Z. Really confusing. In SCIA Engineer itself, you can see the total deflection, the deflection just caused by the variable part of the load, the limit we've defined for each of them, and then the check. Wow, I got the text from my colleague who wants to ruin my presentation. There we go. So I can see then the check values and the overall check of this. As you can see, there's also a camber. In this case, my check is passing, but in case I had a too high unity check, I could either myself define some camber or let SCIA automatically define some camber. Again, this is like the steel settings. So either you can define camber on a global level, you can find it here. You can change the limits for the in-plane and out-of-plane deflection, and you can change the camber definition. So you can say, I don't want camber, I want SCIA to design the camber automatically. So he will put in the camber needed to pass the check. Or you can define your own camber inputted in a parabolic way in a bilinear camber shape, or the camber in case one end is fixed. So I can choose either camber or bilinear for the two-side support beams, and input the camber value I want to use for all the beams. And the same options are also available in the buckling settings menu. So right here, for the deflection, we can choose a camber definition for both. So both in the Z direction and the Y direction. Well, the Y direction, sorry, not in the Y direction, only in the vertical direction can we define camber. Yeah, the other direction would be quite pointless. So here we can choose a camber definition. Either we follow whatever is on in the setup, or we change it here. For this beam in particular, I want to input some relative camber, and I can give it some specific side, and it will be used in the check. Okay, given that we are already at 52 minutes, let me stop talking maybe and see if there is some particular questions. I think I made quite an overview of everything that's specific to American design, doing American design in SCIA Engineer. Anything else works, yeah, pretty much the same regardless of the design code you choose. So doing stability checks, non-linearity, non-linear combinations, doing a second order calculation, all of these things are working the same way for all codes, and I believe some videos can be found as well. So I will not share more details there. Okay. Let me see if there's any questions I can answer. In any case, I want to thank you, those who don't care about the questions and want to leave. I want to thank you for being here. And I hope to see you in the next webinar. I hope the topic was interesting. Don't hesitate to leave me a question or a comment in case there is something you would like to do better, or another webinar you would like to see in the future. And yeah, have a nice rest of the day. If you're leaving us now, I'm also stopping the recording, and then I will answer the questions that are remaining.